Oh, there we go. It's too close. I think I'm too close.
Hello, everyone. And before I start, I want to mention two things.
Nope.
First thing is homework 5. Today is 11th, April 11th. And project I already posted.
Okay.
And
Sure.
you can see that it's a kind of mini project. Much easier than what I have been doing in the past years in this department. I just cut one slice, one segment of the wing. In the past years, we are doing analysis of the whole wing. Okay? So that is why this project is going to be an individual project, not a group project. Everyone has to submit a project report. Okay? I'm going to review maybe after 2 weeks. I'm going to give you a template. What is the format of the project report should be? Okay? Introduction, model, mesh, stress analysis, model analysis, vibration analysis. Vibration analysis we didn't cover yet. I'm going to do that. Okay? So you can start it with the stress analysis already. Build the model, apply the boundary condition, apply the loading, and then plot the stress contour. That is so-called stress analysis. And to help you with the homework 5, that is Buckley. Okay, so I didn't finish the example last time. This is a column. When we apply a compressive loading on the wings, and also we apply a spring in the middle of the column. And the question is to ask you to determine what is a critical compressive loading P when the buckling is happening. So to start with, you need to do a free body diagram. You just take one segment of this column and then plot what is the force and the moment acting on that column. You do the moment balance and the force balance. Okay, this is that segment, and this is what of the force and the moment acting on that segment, and then do a moment balance about this cross section, and this is the equation we have. Okay, so because we are trying to solve what is the deflection, right? What is the deflecting omega Wx? We need to rewrite this m moment into EI d omega x dx. So we need to use this in this equation. Then we can write the equation in terms of Wx. It would be minus EI dx squared plus P Wx minus K Wc 2x equal to 0. So everything is in terms of x now. Wx, and x. And K, capital K is a spring constant, is an elastic constant of that spring. Wc is the deflection at that point. The deflection at here is Wc. The solution for this equation is Wx equals to A cosine dx plus B sine dx plus A Wc 2px. This is a solution of this equation. And you have capital K and small k. This small k is the same as what we have done in the previous 2 examples. It's defined as P divided by EI. This is small k. Okay. So this is the solution, and this one is the constant. You define small k squared is equal to P divided by EI. And then we need to determine what is A, what is B. Right? The constant unknown. We didn't apply the boundary condition yet. So we can apply the boundary condition on this The first boundary condition we can use is the deflection at one end is 0, and deflection at the other end, I should say at the other end is in the middle part. In the middle point is WC, right? And the other one is the rotation at the middle point is 0. Why you have such boundary condition? Because this is the deformed shape. WC is here. WC, this is X, right? So this is a loaded P. A is here. So at this end, there's no deflection. This is the pinning point. If we do not constrain any points, the whole structure will be moving. So you must constrain some points. So you constrain this point, and that means this point there's no any deflection. And you know the deflection at the middle point is given. And also this is the maximum deflection at this point. So that is the derivative of that deflection will be 0. The middle point, two special things. One is the deflection at this point will be maximum, and corresponding to that, we have maximum deflection at this point. That means the first derivative of this deflection will be 0. This one, okay? And this one is constrained. So we have 3 boundary conditions. From the first boundary condition, just use Wx. You have the function form for Wx, right? And now you have boundary conditions. So use the first boundary condition. If you use the first boundary condition, you have the first term, cosine K0 will be 1. So A times 1 will be A. B sine Kx, x equals 0, sine K0 will be 0, so this term will be gone. And x equals 0, so this term will be gone. So if you use the first boundary condition, you only have A times 1 equal to 0, right? Second term and third term are gone. And if you use the second boundary condition, this one is, you have to solve it. From this one, you can solve B equals to WC 1 minus KL 4P sine KL divided by 2. This boundary condition is, you have to solve it. You have to solve, so this one you already figured out A equals to 0, right? And then use the use a function form for Wx, and then use the second boundary condition, you can solve for B. Only one unknown, B, right? So this is a boundary condition for B, and then you can use the third boundary condition to determine what is P. Right now, all of the unknowns are solved already. A is 0, B is this much, it's a function of P. And then you have another boundary condition to use. So you use W dx, x equals to L equals to 0. This is the third boundary condition. From this, you can solve 1 minus 4 From this equation, from this boundary condition, you can form an equation with only one unknown is P. Actually, K is a function of P. Only one unknown in this equation. So you can solve for P. So in textbook, they just give a form like this. You just solve, you didn't finish solving this actually. So PCR will be equal to KL or 1 minus this is a critical loading for this column to have buckling. Actually, from this equation, you will see this equation is not fully, completely solved yet. This is P, but actually small k is also a function of P. Right? If you want to solve for P, this equation, one unknown, one equation. But this is a highly nonlinear equation. It's not that simple to solve for P. There's a P here, there's a P here. There's a tangent of P something. So you have to graph this to figure out what is the critical loading for P. Okay? So this is in hand calculation, you stop here, that'll be fine. Before you have something like this. Okay? You stop here, if you write P into some function into small k, that'll be fine, acceptable. Okay? Because the hand calculation, this is not easy to solve for P yet. Okay, this is a example I didn't finish last time. And today we're going to deal with a more complicated situation. Buckling of columns and bending and also torsion. Because in reality, most likely you will not have bending loading. You will not only have bending loading acting on the beam. Probably you will have torsion simultaneously. If this is the beam, you can have torsion like this. You can have bending like this plane or that plane, right? So if both of the torsion and the bending simultaneously are acting on the beam, what is a critical loading to have buckling? So setup for this column is like this. Okay. Bending constraint, the roller here. And this is compression loading along the axial deformation will give you bending loading. So this is X. And what if you also have a torque P acting on these two ends? And if this is Z, so in terms of buckling and the bending loading, and the compressive loading, the deformed shape could be like this. Right? This is one possibility in XZ plane. So this will give you WX. This is what we have solved. Apply a compressive loading in the beam deformed like this. This is a 3D case. So there's another situation is if you look at the beam in XY plane. This is the beam. You can also deform it like this. This picture is that you look at the beam from the front view in XZ plane. This picture is you look at the beam from the top view. Okay? In XY plane, it can also be bended. Right? So this is a beam. If you apply a compressive loading, you can deform it like this, and you also can deform it like this. In XY plane and the XZ plane, is that both of them are possible, right? Bend it in XY plane and bend it in XZ plane. And another situation is in YZ plane. So what if you look at the beam in YZ plane? This is X, this is Z. Y is along this screen direction. So YZ plane means a cross section, right? You look at this beam from the right view. So in YZ plane, that will depend what is the shape of the cross section. If you have a very complicated shape, a beam like this. This is a cross section of the beam. You look at that beam in YZ plane. And then if you only have bending loading, the cross section will remain as the original shape. But right now you have a torque. So the cross section could be twisted, right? So the deformed shape could be like this. What was the dashed line I plotted here are deformed shape. You can visualize the deformed shape in different plane. You will see different deformed shape, right? In XY plane, in XZ plane, and in YZ plane. If you simultaneously apply bending and torsion, all of the deformation modes are possible. And we should, the final mode should be a combination of all of the three possibilities. So you need three governing equations to govern what is the deformation shape in different plane. This one will be Wx, this one will be Vx. Vx means the deflection along y direction. Wx means the deflection along z direction, and for that one is a twist angle. So we have another unknown to figure out. Alpha x. Alpha x means the twist angle along x direction. X is the length direction. That means each cross section will have a different twist angle. Alpha x is a function of x. Okay. So three unknowns. You need three equations to govern. And the derivation is very tedious. I just give you what is the governing equation. Okay, you just use the governing equation to solve. So the first equation to govern the deformation is EIYY. First order plus T. Second order minus y0. These three unknowns are coupled. Actually, they are not independent of each other. They are simultaneously happening. Deformation along y direction, deformation along z direction, and also twisting. So that means all of the three unknowns should be coupled. You see this equation, you have Wx and also alpha x. I will give you two more equations. You will see alpha x and Vx can simultaneously appear in one equation, and also Wx and Vx can simultaneously appear in one equation. So the second equation will be EIZZ, first order Vx, first order derivative T, second order plus 0. This is the second governing equation. And the third one is very long. So the third one is governing the twist angle. E C W fourth order plus P I0 A minus EJ second order plus P Z0 second order minus Y0 This is the third equation. You will see many constants there. I'm going to explain what is the meaning of CW, what is I0, what is A, what is GJ. Okay, this is the three governing equations because you have three unknowns to solve: Vx, Wx, and alpha x. So you need three equations. And from these three equations, you see many constants. So IYY, IZZ. I don't have to explain. This is a sectional property because you have a cross section of the beam. You can calculate what is the moment of inertia, area of moment of inertia. So you did this many times. And the second thing is what is I0. In the third equation, you see I0 there. So I0 is defined as IYY plus IZZ plus A Y0 square plus Z0 square. Okay. A is the cross section of the area of the cross-section of the beam. And then we see there's y0 and z0. So what is y0, z0? Be careful with this definition. This is the distance between the centroid and the shear center. Okay? Distance between the centroid. Centroid, I mean centroid of the cross section, and the shear center. Okay. And we have another one, CW and G and J. G and E are modulus, so that is for sure. And P is a loading, so we only have this CW and J to identify. So CW is so-called warping coefficient. Warping coefficient. I'm going to do one example, and in homework 5, I give this CW to you, actually. So you don't have to calculate the warping coefficient. I don't know if this is covered in mechanics materials or not. Many professors will not cover this. So I'm going to give this number to you. You don't have to figure out, okay, how I'm supposed to calculate the warping coefficient. Because this is also a sectional property, just like IYY, IZZ. And J is a torsional rigidity. And this is one of the meaning of the constants in those three equations. IYY, IZZ, you should be able to calculate that. Y0, Z0, you should be able to calculate that because centroid and shear center, both of them are covered actually. So you have to figure out what is the shear center, centroid first, and then calculate what is the shear center, and then calculate the distance between these 2 points. You can figure out what is Y0, Z0. And these two are sectional property also. I'm going to do one example. It's also very similar with what I'm going to do in homework. Before I do example, I want to simplify these three equations for this pin beam, because this boundary condition is very easy. It's very simple. You can simplify this equation and then use it directly. So I come back for the setup for this loading P, and also we have a T here, T and here. Let's look at the boundary condition for this beam. Okay? Because this is a pin column, pin beam. The boundary condition we have looked at this boundary condition before. The first boundary condition is Wx at x equal to 0. I mean, this point, this is x. This is x direction. This means the deflection at this point along z direction. This is z. This is x. Along z direction is 0. Right now we are dealing with also deflection along y direction. Right? So this one should be also 0. Y direction is this direction, out of main direction. X, z, inwards. X by z. So this is x, this is z, y is along that direction. So the deflection along y direction should be also 0. And alpha x, x to equal to 0, equal to 0. Torque at this point should be also 0. Imagine torque as a moment. It's a pinning point. It's a pinning constraint. At a pinning constraint, there's no torque. There's no moment. This is what I have. Torque is the same unit with moment. Okay? Pinning constraint means no moment and no torque. So this is so-called torque boundary condition, alpha x. And this is the first 3 sets of boundary condition, and then we have another 3 sets. It's a second derivative dx. How come we have this boundary condition? Second derivative is related with the moment. This means the moment at this point will be 0. The moment about mz, okay? The moment about z-axis will be 0. Similarly, we can have dv, so this is v. dvx, second derivative, dx will be 0. This is from the moment at that point will be 0 about y-axis. And also, second derivative, alpha x this means the torque. This means the torque at the hitting point, which is 0. We have 6 boundary conditions. And we don't know what is the solution for W, V, and alpha yet. But when we look at these boundary conditions, we can assume some functional form which can satisfy these 6 boundary conditions simultaneously. Okay? First derivative, second derivative is 0, and also itself is 0. We can assume some functional form to satisfy this boundary condition first. Put some unknowns in that functional form, and then we figure out what is unknown. So we assume Wx, Vx, and alpha x. Because all of the boundary conditions are written as Wx, Vx, and alpha x. We need to assume some functional form such that this boundary condition can be satisfied. So the most straightforward of the assumption is this one. This is not unique, okay? But we can make the most straightforward assumption. Sine function. When x equal to 0 is 0. No matter what is the coefficient, it will be. Okay? Second derivative for this one. Second derivative for this one will be also a sine x. You have some coefficients, but the function is still sine function. When x equals 0, second derivative for this one will be also 0. The same thing. You can assume the same functional form, okay, but different constants. So this is just assumption. It's not unique. We make this assumption and to figure out what is the critical loading. Okay, so if we substitute, we use this assume the function in those 3 equations. I should come back for those 3 equations. This is the first 2 equations, and this is last one. This one, right? We have 3. No, this one. Where is it? Here. We have 3 equations. We need to figure out what is the 3 unknowns. But we, according to the boundary condition, will assume what is the 3 unknown will be. That is the 3 equations. First one, second one, and this is the third one. Okay. Right now we assume what is Wx and Vx and alpha x, and then we substitute the assumption into these 3 equations. Let's see what's going to happen. So if you substitute that equation, because we are trying to figure out what is C1, C2, and C3, right? If you substitute these 3 functions into those 3 equations, you can get this, P minus EIZZ the first equation you will get, and second equation you will get is P E I Y Y minus P Y0 C3 equal to 0, and the third equation you will have is P0 C1 minus Py0 C2 minus ECW I square L square plus GJ I0 PC3. We assume some functions with some unknowns, C1, C2, C3, and then we substitute those assumptions into those three governing equations. We can simplify that one by one. And those three equations will be in terms of C1, C2, and C3. So we can solve C2, C1, and C3. Actually, we're not trying to solve C2, C1, C3 yet. We can write those three equations into a matrix form. P minus E by ZZ 0, P 0, 0, P minus E I Y minus P y 0, P Z 0, minus P y 0, P GJ minus ECW I squared L squared C1, C2, C3 equal to 0. The first equation we are giving the first column times the first row times this column. That first equation, C1, this one times C1. There's no C2, right? The first equation only in terms of C1 and C3. So you have 0 coefficients here. And the coefficient for C3 will be P0. So the first equation comes from this first row times the first column. Only one column, okay? The second equation comes from this row times that column, and this equation comes from this row times that column. So I just rewrite those three equations in terms matrix form. We're trying to figure out what is C1, C2, C3. We assume a functional form, but we do not know what is the coefficient. So this is the equation for C1, C2, C3. One trivial solution, again, is all of them are 0. And this is the trivial solution. If all of them are 0, it means there's no any deflection. There's no any twist. So that is not what we want. That means if we want to have a non-trivial solution, the coefficients has to be 0. Oh, yeah. The type of address should be here. Yes. Yeah. P should be only associated with this term. Shouldn't be out with the brackets. Thank you. The sign is okay. So this one should be negative, and this one should be, because you have a negative sign here and a negative sign here, so this one should be positive. This one be negative, this one negative. Okay. The sign is okay. Only that P should be in the bracket. Okay. So now the determinant of this coefficient needs to be non-zero. It needs to be 0, sorry. Because this one is non-zero. Right? Something times a non-zero number, you get 0. That means the coefficient has to be 0. So that is how come we have determinant with A has to be 0. We do the Berkeley analysis always like this way, in hand calculation. Always assume some functional form, and we are trying to figure out what is the coefficients. We form a matrix, and then the coefficients, the determinant of that matrix, coefficient matrix has to be 0. And then we can figure out what is P. Because this matrix is in terms of P. You see? P. Every term contains an unknown P. This is a critical loading for this structure to have Berkeley. We're trying to figure out what is P. So when you have determinant this matrix for 0, you can calculate what is P. Before we do that, we make our notation more simple. We define some quantity. Okay, Py is defined as Eyy I squared. This term, I just put a new notation, Py. And Pz, this term, is equal to E IZZ I square L square. I just want to simplify my notation during the determinant calculation. So, and also I'm going to define P alpha equal to A I0 GJ plus ECW I square L square. I define three quantities. This just by definition has nothing to do with duration. After this definition, I can simplify the notation of that matrix. So with that definition, you can simplify that notation in the matrix. The first one is P minus PZ, because you define that term here. So P minus PZ. And this one is 0, and this one is P0. This one is 0. This one becomes P minus P1, right? Because you define one term here. And this one is minus PY0. This one is P0. This one is minus PY0. Not term. Because of that definition, not term becomes I0 divided by A, P minus P alpha. C1, C2, C3. This is just by definition. With this three definition, you can rewrite that matrix. This is P alpha. So you are going to use this matrix for your homework, and probably even exam. Okay, this matrix, because this matrix, the determinant of this matrix is 0. Will give you what is P. Okay, P alpha, Py, Pz are defined like this way. Okay. Do you want an example how to use this matrix to determine P? Okay. If you have a beam with a cross section like this is Y, this is Z. L equals 1 meter. Along x direction. This is just a cross section. YZ, x is along length direction. So, and PR modulus is 70,000 Newton, and shear modulus is 30,000 Newton. And because you are going to need IYY, IZZ, look at that matrix. You are going to need many sectional property. So you will need a geometry related with the section. So the thickness, 2 millimeter, and the thickness here, 2 millimeters. And this one is also 2 millimeters. The width is 100 millimeters. The height is 100 millimeters. So this is a setup. And we need to calculate the bucket loading, PCR. So this is a setup. This is a beam with a cross section like this, 1 meter long. And then you apply a compressive loading along this length direction. I'm asking you to calculate when are you going to have buckling. Because it's very long, very thin, it's very possible for you to have buckling. Okay? It's free to, you need to consider bending and torsion simultaneously. If I'm going to ask you to calculate, to consider bending and torsion simultaneously, I'm asking you to use this equation. If I'm asking you to consider bending only, you don't have to use this, because this equation is for bending and torsion simultaneously. If you only have bending, this is an equation we have introduced in the previous lectures. Okay, just one equation is good enough, Wx. But when you have torsion, you need this. Okay, so what is the critical loading for buckling? The first step, if you want to use that equation, look at that equation, everything seems to be very simple, but actually everything contains lots of information. Even TZ, TY, you need to calculate what is IYY, IZZ, many things. And you need to calculate what is Y0, Y0, Z0. The physical meaning of Y0, Z0 is the distance between the centroid and the shear center. That means the matrix seems to be very simple, but it contains lots of information, geometry information you need to calculate. In essence, this is very easy. If you do not want to do this by hand calculation in your homework, you can build this cross-section in ANSYS and ask ANSYS to calculate all of those quantities for you. ANSYS can calculate the IYY, IZZ, IYZ, Y0, Z0. ANSYS can calculate them very easily. You just click one button. What is the section property? We will list that section property for you. But in hand calculation, you need to do that. You need to know what is IYY, IZZ, and what is the shear center. So the first step, because we need to figure out what is the centroid, right? We need to calculate what is the distance between centroid and shear center. So the first step is to calculate centroid, Y, Z. Because it's symmetry about y-axis, that means the centroid of this cross-section must be along y-axis. But we don't know what is the distance of this much. So this is the first step. You need to calculate that distance. That distance, actually, I just did the equation for you. You did this many times, I believe. This is the total area. This is the total area, right? Top flange, bottom flange, and web. Thickness times the length. 2 times 100, 2 times 100, total area, right? And then it's equal to do that part by part. So 2 times 2 times 100 times 50. This is YC. Suppose this distance is YC. Okay, this is the formula for us to calculate what is the centroid of this cross section. Because in this coordinates, you need to calculate the total area times that centroid and equals to the area of that area, summation of the area by area. So this one will give you YC equals to 33. How to calculate the centroid? You did this many times. I believe you know how to do that. And second step is the distance between the centroid and the shear center. So right now you figure out, okay, this is Y, this is Z. This is YC. Centroid is up here. Shear center could be up here. How to calculate shear center is not easy. In 321, I put this in final exam. Many students cannot finish in 1 hour. So shear center takes you maybe, for this cross-section, takes you more than 1 hour, even 2 hours to figure out what is the shear center. You have to figure out what is shear flow, and then do the moment balance. This is what we did in 321, right? First step, figure out what is shear flow, and then the shear force acting on the shear center should be balanced by the shear flow, moment balance. This is the procedure we calculate shear center. So in homework or final exam in this class, I will skip this for you, because shear center only is even very tedious already. Okay? Shear center, how to calculate the shear center of this cross section, you have to go back to check your notes on 321. And actually the solution for this is 76.2. The shear center from here to here is 70. Let me check. Is from the origin from here to here, the distance. This is my calculation. Actually, this shear center I calculated in the I put the origin in the centroid of this cross section and then calculate the shear center, and the distance between the centroid and shear center is this much. Okay, 76.2. And it's negative actually. In my notes I put a negative. That is why you confused me, because it's along negative y direction. This is origin. From here to here is negative 76.2. But in the calculation, you are going to need the distance only, so negative positive doesn't matter much. Y0, Z0, Z0 is 0. This is distance between the shear center and the centroid. This is the centroid, this is the shear center. And then, when you go back to check that matrix, another quantity you need is IYY, IZZ. Right? IYY, IZZ. I'm trying to use this matrix, but before I use that matrix, I'm calculating term by term. Y0, Z0, calculate first. And then IYY, IZZ, because it is contained in PZ and PY. So I need to calculate the sectional property of this cross section. So IYY will be in exam 2. I also asked you to calculate the IYY and IZZ of that fuselage. So this is the same procedure, just area times distance squared. Okay, IZZ will be I0, because when you look at that matrix, you not only have PY, PT, you have the I0 there. So according to the definition, I0 is equal to IYY plus IZZ plus A Y squared plus Z squared. Right now you have everything. IYY, IZZ is there, Y0, Z0 is here, A is the area of that cross section. So I0 will be 5.35 and 6. This is the most tedious part actually. After you finish this calculation, you use that matrix. It's very straightforward. Before you use that, you have two more constants. This one and this one. This is so-called warping coefficient. This one I'm going to give you. And this J is the torsion rigidity of this cross section. So torsion rigidity, actually we have a formula in 321. I give you a torsion rigidity formula in 321. If you forget it, you can go back to check, but in homework I gave this to you already. What is torsion rigidity? Okay? It's also quite straightforward for this cross section. It's 800. So these two, one is warping coefficient. If you really want to figure out, okay, what is a warping coefficient, you just check the textbook in 321 or mechanics materials, or even Google, you can figure out, you can find it. And what is torsion rigidity? So you will have some formula for this too. Now you have everything prepared, just like cooking, right? You prepare many things first, and then the cooking really just takes you a few minutes. But before you're cooking any food, you have to prepare many recipes. According to the recipe, you have to prepare many materials first. This is the materials you are going to need. Okay, and then you use that matrix. I'm going to stop here. Okay, next time I'm going to continue to figure out what is critical loading for P. But everything is prepared already. In homework, you have very similar problem like this.